For Lab 3, the goal was to visualize the magnetic field due to a bar magnet at multiple observation locations, to find the distance dependence of the magnetic field from a bar magnet, and to use experimental procedures to find the dipole moment of a real-life bar magnet and the magnetic field due to it. These are the fundamental physics principles. In this experiment, we had to find the magnetic field due to a dipole magnet, and we also had to take into account the magnetic field due to the Earth. Moving electrical charges create magnetic fields around them, which influences other moving electric charges. The dipole magnet and the Earth are both sources of magnetic fields. We use the Biot-Savart law for a dipole magnet, which finds the magnetic field due to the magnet. This general formula is shown. And we also examine the distance dependence of a bar magnet's magnetic field. This describes how the magnitude of the magnetic field is influenced by how far away the observation location is from the magnet. Now for a brief overview, I first examined how the magnetic field due to a magnet changes at different on-axis distances from the magnet. I then was able to find the dipole moment of the bar magnet and the magnetic field due to the bar magnet at an observation location that was at a 45-degree angle from the x-axis. And finally, I used GlowScript to make a computational model of the bar magnet and its magnetic field. Before I began the experiment, I had to use the magnetometer to find the Earth's magnetic north-south axis. I zeroed out the x-component of the field, and this direction was the north-south axis. The meter-stick placed perpendicular was the east-west axis. For the first experiment, I had to examine a distance dependence. I measured the distances the magnetic sensor was from the magnet when the magnetic field's x-component was about 20, 70, 120, 170, and 220 microteslas, and I observed that as the magnetometer got closer to the magnetic field's x-component got larger, and when far away from the magnet, the x-component was close to zero. I recorded these average distances. Then I graphed the natural log of the distance versus the natural log of the x-component field, which is shown along with the line of best fit. We use the natural log instead of just graphing distance versus field because it helps us better visualize the relationship between the distance and the field. The distance dependence equation, k constant r to the n, is shown along with the on-axis formula for the magnetic field due to a magnetic dipole. These two equations should be equivalent. The k represents the constants of the on-axis formula, the r is the distance, and the n of the exponent of r, if the experiment was done correctly, should be about 3, like it is in the on-axis formula. I found n for the distance dependence, which was the slope of the line of best fit from the graph, to be fairly close to 3, and I found the k constant from the line of best fit, which I set equal to the constants from the magnetic field formula to find the dipole moment. These calculations are shown. Then for the off-axis experiment, I first found the on-axis distance d perp from the magnet when the net magnetic field was 100 microteslas, and I recorded the y-component at this on-axis distance, which represented the Earth's magnetic field, since along that axis, the magnetic field due to the magnet would only be in the horizontal direction, and the magnetic field due to the Earth would be in the vertical direction. I then moved the magnetometer up a distance d perp, so it was at an angle of 45 degrees from the magnet. I recorded the components. However, at this observation location, as shown in the right picture, the vertical component would be from both the magnet and the Earth. So to get the y-component of the magnetic fields due solely to the dipole magnet, I subtracted out the Earth's magnetic field I measured before. Then I was able to find the magnitude of the magnetic field due to the magnet to be 3.8 times 10 to the negative 5 teslas. For the coding, I started by establishing the dipole moment that I found during the experiment. I then wrote a function that would calculate the magnetic field at a location due to the dipole magnet. I wrote code that would calculate the magnetic field at 6 different locations, 2 on-axis and 4 perpendicular. The picture here shows how I found the field at observation location 1, and I did the same for the other 5 locations. I then wrote code that would find the magnetic field at a location 45 degrees from the magnet and a distance d away from the magnet, d being the distance I measured in the experiment. The code displays the magnetic field at these different locations. The cylindrical object in the center is the dipole magnet, the orange arrows are the on-axis locations, and the blue are the perpendicular locations, and the purple is the off-axis 45-degree angle location. My two values for the magnetic field at 45 degrees were very different. This could be because in the experiment I measured a z component of the field, while in the computational model the z component was 0. Also, in real life, there could have been other magnetic fields from nearby objects, while the computational model only took into account the field from the dipole. To conclude, if I hadn't oriented my experiment to compensate for magnetic north, the magnetic field from the dipole magnet and its dipole moment would still be the same no matter the axis, but it would have been much more difficult to find these results. This is because the net field X component would then be the sum of the X components of both the Earth's and dipole's magnetic fields, and the net field Y component would be the sum of the Y components of both the Earth's and magnet's magnetic fields. With the way this lab was done, when finding the on-axis field, the X component was solely from the magnet, and the Y component was solely from the Earth. Finally, if I were to stick two identical magnets together, the magnetic field would still be in the same direction, but the magnitude would be larger. This is because the magnetometer would still be the same distance from the north side of the dipole magnet, but the south side, now further away, would have a lesser effect. Thank you.